Okay, are there any questions before I begin? I'm kind of not at all prepared today because I had been having meetings and trying to finish some reports and stuff. So I'm going to kind of wing it. But from what I remember, last lecture, we looked at the Navier-Stokes equation and how we solved the Navier-Stokes equation in using COMSOL. For channel flow, we looked at concepts of entry length and boundary layer development. And then we moved on to various types of boundary conditions and started playing with COMSOL to set up problems. And the so-called laminar flow in two-dimensional channels. What I want to do today is continue with the COMSOL demonstration in using axisymmetric flow. What does that axisymmetric flow mean? What are the situations where we can solve that problem, and what equations do they solve? And then we'll switch back to the theory portion of it, where I will go through an exercise of cataloging all the model equations that are available in COMSOL and in ANSYS. So I've taken the material from ANSYS for the lectures. This is still in the second phase of the course. We're looking at various types of models for single-phase flow, for multi-phase flow, for turbulent flow, etc. Then we'll come back and look at the concepts behind turbulent flows and multi-phase flows, the averaging concepts. Right now, we got involved in developing the Navier-Stokes equation, and we're going to look at all the equations that fall within the class of Navier-Stokes equation, an advection diffusion formulation with a pressure velocity coupling. And how does COMSOL solve it? How does Fluent solve it, etc., to get a feel for that. So I'm kind of organizing the course this time. This is probably the third time I'm teaching it, but in a slightly different form. I'm experimenting still with what logic flows well in terms of grasping the material. Okay, I'm not sure that there is a perfect logical sequence yet. So you need to give me some feedback in terms of whether you feel whether I'm going in and out of various topics, and does that create a confusion in your mind, or is the progression logical? It makes sense to you. Okay. Any questions, comments, feedback? I'm also working on your next assignment, and then I should finish the grading of the first two assignments. The project list is still not completed. I'm kind of behind, but I will adjust the scope of the project so that you will still have time to do it in two phases. One is literature review and formulation of the problem over a period of 4 to 5 weeks, and then solution over the next period of 4 to 5 weeks or so for one particular problem in that paper that I recommend, or the paper that you choose if you're proposing the problem. But I will get that to you certainly this week. I'm glad actually that my trip to Houston was canceled, so I can catch up on this course. So I'm going to open up COMSOL. Any questions before I do that? Where is COMSOL? Yeah? You found it? Where is it?
Right below my lateral. Yeah, like
there. So any questions from last lecture? The type of problems that we set up in COMSOL for two-dimensional Navier-Stokes equation, two velocity fields, pressure field, okay, in any geometry. So we saw how nicely it is laid out. The geometry building is separated but integrated into the software framework, so you can actually go in and build simple geometries. But if you have more complicated three-dimensional geometries, the selection process of building the physics, importing the geometry would be a bit more difficult. We can still build 3D geometries within COMSOL, but you can also import them directly from other CAD programs. And once you do that, meshing is the same, setting the boundary conditions will be the same. Boundary conditions in the 2D case are lines. Boundary conditions in 3D cases would be surfaces, right? So you need to identify surfaces bounding the 3D domain and identify what are the values for various variables. So let's go through the model wizard. This time I'm going to pick 2D axisymmetric. So if you see, we started with 0D, 1D, 1D axisymmetric we didn't do, but you can easily figure out how that would be. And then 2D, so it is 2D axisymmetric. The problem I'm going to do today, I lost my pen that writes on this, but let me see whether I can write with my finger. The problem I'm going to discuss today is a so-called Taylor-Couette flow. But there are a number of other problems that one could set up as well. Okay. Does it let me do? I think I have the calibration problem again. Okay. Okay, so this is the axis. What you see.
Rotate the projector a little bit so we can get the whole picture inside the screen. Is it okay if I try?
You can try, but be careful. Somebody has to hold your chair. That's an engineer. Okay, so the geometry I'm going to consider is two concentric cylinders. Okay, I'm showing you a cut section of that, and this is your axis. Okay, so going around this line, if you take this rectangle and rotate it around 360 degrees, you will form a concentric annulus. So that annulus is filled with a liquid, and so it is two-dimensional in the sense that this is your radial direction, okay, R, and that is your Z direction, axis. And going around it, there is a theta direction. So if you know cylindrical coordinates, you know how the Navier-Stokes equation looks in the cylindrical coordinates. I will show you later on when you go back to the PowerPoint slides. So what I'm going to focus now is on how would the flow look to set up the problem for a domain that is a concentric cylinder that is completely filled with liquid. This device is a very important device, and this problem was studied by Taylor in the 1927, and I think I probably showed you in the last lecture a lot of flow patterns that were computed in this particular geometry. But it is also used in viscometer. Why is it useful to measure viscosity? Because if you take the inner cylinder and rotate it by mounting it on a motor at a constant speed, that creates a flow field between the inner cylinder and the outer cylinder. Then mount the outer cylinder on a torsion bar. So the outer cylinder, from its equilibrium, it is stationary, but from its equilibrium position, when there is no flow, it will tilt a little bit when the flow is there. And the extent to which it will tilt depends on the rotational speed. Okay? And you put a bar on the top side to see how far the needle moves. And then from the torsion in the rod that connects to it, you can measure what the torque is. Once you know the torque multiplied by the arm length, that gives you the force, gives you the shear stress. Remember, for Newton's law of viscosity, you need to know the shear stress, you need to know the shear rate. Then the viscosity is your proportionality constant. So from the torsion bar, you get your shear stress. From the rotational speed, you get your shear rate, and then you can back calculate what the viscosity is. It's a very commonly used viscometer. But you need to make sure that the velocity field that you get inside for viscometric measurement must be linear. Okay, the velocity profile should be something like this, meaning the inner cylinder rotates at r omega, so the velocity there at the inner cylinder is r omega, the velocity at the outer cylinder is 0 because it is fixed, and in between the velocity is a linear profile. If you operate in that domain, then you get a simple relationship between shear stress and shear rate. But if you rotate the inner cylinder faster and faster and faster, that's going to be your next assignment. you'll find that that flow becomes unstable and you get into a transition where these cells form. A lot of these cells that are uniformly spaced. Okay, and that is a 2D axisymmetric flow. And we are going to try to set up towards that. So I'm going to show you how to do that, but we won't succeed into the transition because that takes a lot of iterations. You need to, that would be your challenge in the assignment. Okay, any questions on the Taylor-Court flow? The problem we are going to look at is a 2D axisymmetric problem. And let me ask you a question at this stage. And if, let me see whether I can do that. Okay. I should buy a pen, I think. This is terrible. Let me go back to for axisymmetric flows, what should the velocity field look like? Okay, so if V is the velocity field, which is a function of R, let me do it. Velocity is a function of R, theta, and the Z. Okay, so the velocity field is going to be a vector. It will have all three components, and they're going to be function of R, theta, Z in general. But axisymmetry means what? Axisymmetry means there is no theta dependent, so that goes out. Okay, and in terms of components, when you're expanding this, you're going to have VR as a function of R and Z. Okay, and VZ as a function of R and Z. How would V theta? Will the V theta component be 0 or non-zero? V theta will also be a function of R and Z. So what would you call such a flow? I guess I had it. Is it 2D? Well, you call it 2D axisymmetric for a good reason, right? But there are three velocity components, okay? But they are functions only of two spatial variables, R and Z. If you go in the radial direction, the velocity changes. If you go in the axial direction, it changes. Angular direction, it doesn't change. Any plane you cut, it's exactly the same. But there are three velocity components. How does this differ from 2D planar flows? In 2D planar flows that we saw flow between two parallel plates, we had two velocity components, but they were functions of only two spatial positions. There was no third velocity component. Okay? That's how the 2D axisymmetric differs from 2D planar flow. And that's why they have a separate model for building axisymmetric flows. With this flow, you can study a large number of problems. For example, if I'm interested in studying flow past a sphere that is placed in a channel, I might actually make this as one of the assignments in the future. Right? So I have a cylinder and I place a sphere. How would I model this in a COMSOL? Can I do this? This is my axis. This is my semicircle. And that is my line. Right? So I build these two geometries, a semicircle and a rectangle. And I subtract this out. Remember, there are Boolean operations in COMSOL, right? So you subtract one from the other, and your flow domain is essentially this. And these are all, this is axisymmetry, this is all solid, and that's all solid. And this is inlet, and that is outlet, right? All you have to do is, if you rotate that around that axis, you're going to get a sphere in the middle and a pipe around surrounding it. So you will pick, once again, 2D axisymmetric mode and build that geometry. Okay? Is that clear? Okay, so
So we have a theta component of velocity, but it's constant.
that's a good question, right? In this particular Taylor-Court flow problem, I'm glad that you brought it up. I was going to bring it up later. But in the Taylor-Court flow problem where you have two concentric cylinders, you will have all three velocity components, right? In the angular direction also there will be a non-zero velocity component. How about in this problem? So if you have to identify what are the velocity components that are non-zero, so you would say this is R, this is Z, and theta would be around that, right? So this velocity vector V, there will be VR as a function of R and Z.
You have a cutoff actually in this case. You have a cutoff. So R away from the sphere, there is no theta component. Just near the sphere, there will be a.
Think about it carefully. So you are saying near this, there will be a theta component.
So no, there will be no data. There will be no data. Yeah, there won't be a data.
That's a very, very refined answer to that question. Yeah, you're absolutely right. In laminar flow, you won't have a theta component because as the fluid comes and hits this, imagine this is the sphere, it's going to go around it in the same way in all directions, right? So if you take a cut about the axis anywhere, you will see the same picture, okay? But in turbulent flow, that's not true. In turbulent flow, it breaks all symmetries that are in the geometry. And that's why you will have all components. So in turbulent flow, you need to solve all components with time also included in your Navier-Stokes equation. If you're doing it by DNS, direct numerical simulation. Okay? But for laminar flow, you will just have VR and VZ as a function of RZ. So it's actually, I'm glad that this example came up by kind of fluke. I wasn't planning to talk about this. There is a checkbox that you will see when you're building the axisymmetric one. One is without a swirl, the other one is with a swirl. This one is without a swirl flow because there is no component in this direction. Whereas the Taylor-Court flow is axisymmetric with a swirl flow. That means it has to write down the third momentum equation in the angular direction. In this case, it will just solve two momentum equations, R and Z. It will not solve the theta momentum equation. Okay? Is that clear? Now, if I say that this sphere is rotating at a certain angular velocity, then you will invoke swirl flow immediately. Or if I say that the outer cylinder is rotating at a certain angular velocity, you will invoke. So it is the forcing from the boundaries that determine what type of flow will evolve inside. Okay? So in the Taylor-Court flow, in fact, it is through the instability that it develops the type of velocity component that we saw. I'm sorry, these things are not captured on the notes, but this is the geometry for Taylor-Court flow, right? So we said in this case, V is going to be equal to VR as a function of R and Z, and V theta as a function of R and Z, and Vz as a function of R and Z. But that is only after it passes through the instability and these cells form. If the rotational speed is very, very low, then what you find is actually a 1D flow. Okay? That is, V is just a function of V theta as a function of R. Just R. If it is an infinitely long cylinder, it is just a function of R. That is, the velocity profile will look something like this. But it will be the same at any section in Z, and it will be the same any section in theta. So this is a case where the symmetry is invariant for translation and for rotation. That's a 1D flow. Okay? And that spontaneously becomes unstable, and you get this 2D axisymmetric flow. If you keep increasing the rotational speed, this also becomes unstable. And then you will get a 3D transient flow towards turbulence. All will happen in the same geometry depending on the degree of forcing that you have, the Reynolds number or the Taylor number. Okay, so for the physics, let's pick laminar flow. Add. And we are done. So we picked 2D axisymmetric and laminar flow, right? So we need to build a geometry. So immediately, the moment you pick axisymmetric, it shows the axis, the orientation. Okay? So R equal to 0 is the dashed line. And so that gives you an idea of where to put your geometry. Okay? So if I take a rectangle and then and I can position it any way I want, so I'm going to say 0.2 and height is 2, and let me position it at the center and build, center it. So it is a very narrow cylinder, long narrow cylinder with the center placed somewhere here. Where is it? No, it's here. Why is the center? R is 0.3 and Z is 0. I want 0, right? Okay. Right. So I wanted to place the center right in the middle of the geometry. Okay. And it's at 0.1, 0.2, 0.3. Okay. And I'm going to put a fluid inside. That means I need to identify its properties and I need to identify its boundary conditions. And you are going to help me in formulating this problem. The problem I want to solve. Question, yeah?
Do you have the option to change the direction of symmetry axis to z equal to something?
No. That's what COMSOL does, and I think Fluent also has
So
some
if
sort
you
of.
want to see effect of gravity or some problem that.
Good question. Please keep raising these questions. Okay, that's an important question. Okay, just because the geometry is vertical, that doesn't mean gravity is in the vertical direction, right? You can put the gravity vector any way that you want. So when you have G, you're going to give 3 numbers, which are components of the gravity vector, and each component will be added to the respective component of the Navier-Stokes equation. Okay, so you can do with respect to gravity any way that you want by simply putting the gravitational vector, but this is the axis that it picks arbitrarily. Okay. Any other questions? See, these are questions that really give you a practical insight on how to go about formulating various problems, and through assignments we will reinforce that. Okay, so we have the problem I want to solve is concentric cylinder, infinitely long cylinder, so you need to keep that in mind. And I want to first generate the 1D flow and then see whether I can force it into the 2D flow. I'm going to have difficulty in convergence, but you will know how to set it up. Okay, so fluid properties. Those are routine. We have already seen that. User defined. I'm going to put 1. Viscosity. We can do non-Newtonian, etc., but let's just take user defined and make it 1. Okay, so density is 1, viscosity is 1, the channel width is 0.25 or something like that, 0.2. So you get a rough idea what the Reynolds number is going to be. Okay, I want to pick my angular velocity in such a way Reynolds number is of order 1. Laminar flow, it will converge very quickly. Okay, and then I'm going to lower my viscosity to increase the Reynolds number and see what happens to the flow. Okay, so that's done. Initial values, by default, they're all set to 0. Now I have a problem. Because I defined as 2D axis symmetric, it has only 2 velocity components, ur and uz, r and z. Right? How do I invoke the swirl flow component? Because in this particular problem, swirl flow is present, right? So you go to the laminar flow, and there it is, swirl flow. You check that box. Do you see it here? Down. So that activates the third momentum equation in the angular momentum direction. Okay. Now, if you go and pick your initial values, you will find that there are 3 entries automatically for you. Okay. Or phi is what they call the angular direction, and then initially it's initialized to 0. That's fine. We can live with that. But axial symmetry. You need boundary conditions, right? So the axial symmetry is a folder, but it simply says that there are 4 boundaries for this problem. None of them are manipulatable from the axisymmetry folder. Okay, but you need wall. So here wall boundary condition is built in, but you can by default all 4 bounding domains are taken to be wall. Okay, they're all there, but you have to override them. Okay, and what would you like to override? In the inner and outer can be wall. How about the top and the bottom?
It's infinite, right? So you
It's
have
infinite. So how do you simulate the infinite boundary condition is the question.
periodic boundary condition.
Periodic is one. Now you need to understand the concept of periodicity, right? What does periodicity mean? What does symmetry mean? And how does it relate to the infinitely long? Because computationally we cannot do infinitely long, right? So we need to take a finite domain and mimic what would happen in an infinite domain, okay? So in an infinite domain simply means that all the gradients in the z direction should be 0. But by picking this, I have allowed all these quantities to be non-zero in the momentum equation. So the equation it's going to solve will involve Vr times dVr dz, for example. Okay? But I need to force it in such a way that there is no variation in the z direction. So all those derivatives spontaneously go to 0 if there is no forcing, right? There is forcing in the radial direction because I'm going to rotate the inner cylinder. Outer cylinder is fixed. So the dependence of all these velocities on r are enforced from outside. If I go and say solve right now, what did it give you? 0 everywhere. It will satisfy that, right? All the boundaries are 0. The fluid initially at 0. And the Navier-Stokes equation, left-hand side, right-hand side, everything is 0. It is satisfied. 0 is a solution, valid solution to Navier-Stokes equation, but there is no forcing. So it is the forcing that causes the flow. Forcing from the boundary or forcing as a body force, the rho g term. Okay? But rho g term in incompressible flow is tricky because if it is hydrostatically balanced, then there is no flow arising out of it. Okay? But if you have, for example, heating from one boundary, can you create a flow inside? Answer is yes, because if you're heating from one boundary and cooling from the other boundary, the density near the hot wall is going to go down, and so gravity will then start raising it up if you put g in the vertical direction. Okay, so you can set up a density gradient in a gravitational field and drive that. In that case, the driving comes from the rho g term, or typically the driving comes from the boundary condition, right? So in this case, I'm going to pick the top boundary. No, I want to create a boundary condition for symmetry. Okay, and I will create 2 of them. Well, I guess I'm going to try something now. Can I, in one folder, can I identify both of them as, I guess it allows you to do that, right? So you have one symmetry folder, and you identify top and bottom as symmetry boundary conditions. Now, when you have symmetry boundary condition, what does it actually imply? What equation does it impose, right? The beauty about COMSOL is that it shows you what is the condition, precise condition that is imposed on that. Can you decipher this condition? What does it mean? What does this mean? Q dot n equal to 0.
Velocity in the normal direction.
Velocity in the normal direction, that is, velocity crossing this, is 0. That means there is no velocity on the boundary crossing it. Okay. The next equation, what does that tell you? K is defined as mu times del u del u transpose. That is the stress tensor, right? So there is no tangential stress that is imposed on these boundaries. Okay, because what you're doing is you're dotting K with n, and that's subtracting from K. That is taking the normal component, subtracting from K. What is left behind is the tangential component, right? So the tangential component of the stresses are 0. Tangential component of the stresses are dependent on the velocity gradients in the other direction. So the velocity gradients are 0. The velocity is 0, the velocity gradients are 0. So there is really no forcing from the two ends. Okay? Any question on that? So this is really, we are talking about tight coupling and developing a feeling for how do fluids move and how do we simulate those. Okay? So that one, and then the other one is wall. But I want to create 2 walls. Why would I want to create 2 walls? Because I don't want both of them to subject to the same 0 condition. Okay? So I'm going to go back to the laminar flow and pick another wall. Okay? So wall 1 is the outer wall, and wall 2 is the inner wall. Okay? And here the equation is u equal to 0. And if I say, what do I pick from these? you need to slowly get used to what are the options and what do they mean, or at least guessing about what it means. Because no slip means the velocity is 0. You don't want no slip at the inner wall, right? It is in a sense no slip because there is no slip between the wall, but the wall is moving. You need to enforce that. So they give you an option for that: sliding wall, moving wall, leaking wall. What does a leaking wall could mean? Porous wall. There's a normal velocity component, right? Now a moving wall would be a piston that moves perpendicular to this. A sliding wall is a tangential motion. Okay?
But does it still have no slip as a
I strictly think that it is still no slip, right? A sliding wall, but the fluid sticks to that sliding wall. So there is no slip between the fluid and the wall in a strict sense, right? That's why the fluid moves with the wall. Okay, but in their terminology, no slip means velocity is 0. Velocity difference 0 is a more precise way of saying it for no slip condition.
What is the slip velocity?
Slip velocity you need to pick and specify.
So, I actually have a question. So,
Yeah.
there is a threshold over which the fluid would actually slip over this, which you can only find out through computation sometimes. Would slip over the wall if it's too fast.
As long as the Knudsen number criterion is satisfied, that means there are enough molecules between collision, you will not have a slip condition. Okay, so the slip condition occurs under extremely rarefied gas. So this is gases in catalyst pores, nanopores size scale. Then you will have Knudsen diffusion and you will have slip at the wall. The other example that we talked about is when you have long polymeric chains where the length is fairly significant and one end gets stuck, the other end is inside, then it exhibits stick slip kind of a phenomena. And those can be discovered from a fundamental sense by MD simulations, molecular dynamic simulations. But on a macroscopic observation, you just discover their presence by looking at macroscopic flow rate versus pressure drop relationship. Okay? Any questions? So what do we have as options? Sliding wall. So the moment I change the sliding wall, it says U is equal to UWT. T is the tangent vector. Remember, if you have a surface that is moving, there is only one normal to the surface, but there are two tangents that are perpendicular to each other, right? So tangent on a surface is a vector with two components, which you can resolve in any way that you want. Okay? So this condition simply says that some magnitude of the velocity, moving wall, the sliding wall velocity, and the direction in which it is sliding, the tangent vector. So the tangent vector is actually split for you into two ways, right? So velocity of the tangentially moving wall, velocity of moving wall, phi component. That's what we need to specify, right? Because it is having only phi component, right? So we can put in a value. What value you want to put in? Maybe 1. Just to get you started, right? You can put any value that you want. In an assignment, I will say, generate this result and compare the analytical result. Then you need to find out exactly what values to put in for that result. But I'm just demonstrating as a placeholder. But if it is 1, it is meter per second. So you can actually calculate what the angular velocity would be for this, because you know the radian distance, right? Omega times r is this number. Okay, in the tangential direction. Okay, so that's how simple it is. The same framework, yeah.
I didn't understand the velocity of the tangential moving wall. What is it?
You can move in the z direction also.
Yeah. So, as you will have a wall that is, this is an important problem in coating, wire coating, for example. You have a wire that is being pulled to coat the wire. So this is the central part, right? And you're pulling it, but you're immersing it in a polymer. You want to coat that. So as you're pulling it, this has a velocity like this. And then what would be the velocity profile look like? Okay? This is why I said on any surface, there is one normal, but there are two tangents. In this case, one tangent is in the z direction, the other tangent is in the phi direction. Okay, so you need to identify what are the two components there.
So what if the wire is moving normal to the plane? Like we can do that only in the 3D.
Good question, right? Did you understand the question? What happens if you're moving the wire perpendicular to the board? Okay, it has now a translational velocity, right? But it is not axisymmetric anymore, and it is truly 3D, and it is. You should know which method would work for that. We are going to talk about it later in the course. Inverse boundary method. You need that formalism to be able to. This is an important problem too. Stirrers in CSTR, for example, you have various impellers that are all moving. You can have them in very complicated motion, right? So there is a whole class of method called inverse boundary methods that it's an algorithm that imposes the complex motion on a fluid with an immersed boundary. The boundary is immersed in the fluid, undergoing arbitrary motion. So there is a pneumatic pumps, so-called Moino pumps that have complex structures that pump the slurries, for example. So CFD in all these areas are being extended very rapidly, and all we are doing is understanding the basic fundamental concepts of imposing boundary conditions, and progressively we will make it complicated to look at turbulent flow issues and multiphase flow issues. But I'm glad that you guys are thinking and extending this beyond and trying to find answers to this. So the purpose of this course ultimately would be to know the art of the possible, what is possible in the computational domain, in the continuum mechanics field. And once you're aware of that, if you have a need, you know where to go and how to set up the problem. Any other questions? Do you think I have specified all the issues? I haven't built the mesh, but if I go and say solve, surprisingly, it will just go and mesh it and then solve it automatically, okay? But I don't exercise any control over the mesh.
You have to specify the boundary of the other
I think it's a no slip.
That one is by default
right?
no slip, because that's the only. See, when I built the model, initially it put this equation and it put this folder and identified all four as one. Then I put these two folders and overrode those specifications. That's why it has overridden. But 4 is not overridden. 4 was originally as it was, wall with the no slip condition 0. So I don't have to worry about it. But in the literature, people have studied, including Taylor, 2 cylinders that are rotating in opposite direction, 2 cylinders that are rotating in the same direction. All these are possible. Here is a question for you to think about. If both are rotating at the same direction, in same angular velocity, what would you expect the fluid to be in between? Hmm?
Have a profile. Like,
So we'll have that 1D profile.
We will have this 1D profile.
moving conditions at both the walls.
Mm-hmm.
So the fluid layer in the middle would be having the minimum velocity.
Angular velocity.
Same angular velocity.
So
Yeah.
it's like it depends on your center. What center are you look like? If your coordinates are moving, like with the same angular velocity.
The coordinates are not moving. The coordinates are fixed, laboratory coordinates.
So
You still have a parabolic region, but just with the minimum and
no, it's really same thing happens.
if it's at same it's at same angular momentum, there will be a minimum at the center of the two walls.
Why would you have a minimum at the center?
Because if it's laminar
Okay,
flow,
not necessarily the center.
the resistant layer would just go down.
Because the velocity profile would be linear.
The radius is
velocity in
different.
the direction of theta, but it's constant. Like
Omega is constant, radius is not constant.
Right. So if you plot the linear velocity, how would it look? If you plot the angular velocity, how would it look between these two? Okay. So
Angular
this
velocity-
is R1 omega 1 This is R2 omega 1. They're both at the same angular velocity. So this wall is moving at R1 omega 1, this one is moving at R2 omega 1. I think some of you guys are hitting on this minima, but I know where that thought is coming from. So to clarify that, I will tell you that this cylinder is filled with a liquid. Initially, it is at rest, and at time t0, I start moving it. Both of them at the same angular velocity. They are both mounted to the same motor, right? And it is moving with omega 1. That should give you some clarity to your thinking.
So somewhere in between R1 and R2, we have a minimum. That's all I can say.
A minimum in what?
Minimum the velocity along with the direction.
So
The angular velocity
it's
is
like
same the
yes.
entire distance. Well, yeah, the velocity profile, which is R omega is fixed, but R is changing. So yeah,
Yes.
The
So
linear
it should look
velocity
like
changes.
this.
but basically the entire thing is rotating.
How many of you agree that it should be just a linear R omega? Very under steady state conditions. You have to be
If
precise.
it's angular, and the angular momentum is constant, well, angular velocity at both points should be the same.
Yeah, so you
And it has to decrease from that point inwards on both sides.
No, but the angular velocity anywhere is omega times r. If it is in a solid body rotation, with the entire fluid, that's the key that I'm trying to get at, whether you will spontaneously lock into, right? If the whole fluid is a solid body rotation, that would mean that the velocity profile has to be something like this. This value will be omega 1 r1, this will be omega 2 r1. Because the whole thing is moving as a rigid body. Okay? But if I put this additional constraint that says that the fluid was initially at rest and I start moving the two cylinders, the moment I start moving the cylinders, the fluid next to it will start moving with that velocity, right? But the fluid at the center should be
That's stationary.
at stationary. That's when you will get your minimum,
Yeah,
right?
that's-
So the profile would be something like this.
Yeah, that's what I was thinking.
At a very short time.
at the start.
You wait a little longer, keep rotating it, that momentum diffusion will take place from both sides. So it will become like this. You wait a little longer, it will become like this. And then it will become like that. And eventually it reaches the state, and then it stays there.
So that is V theta R, right?
Hmm?
So it is only V theta.
This is only V theta as a function of R.
Yeah, 1D.
1D. It's essentially 1D. Okay? 1D steady state is this. 1D transient will be something like this.
So after it reaches steady state, the minimum velocity would be at one of the
The minimum velocity would be at the left end. If this is, if both are at the same angular velocity,
Okay.
omega times R1 is less than omega 1 times R2.
even if the distance between R1 and R2 is infinitely long.
Yeah.
So the time will be longer.
The time it takes to reach steady state will be longer.
Okay.
Right? Does that make sense?
Yes.
A lot of the intuitive thinking is necessary to set up the problem right. Okay? Now I'm going to put a twist on this. Okay? Initially at 0, the fluid is at 0, and start rotating this at omega 1 r1, and I start rotating this at omega 2 r2. They are different, but omega 1 is faster than omega 2. Okay, what would the profile look like?
Depends on R1 and R2.
Hmm?
The magnitude of R1 and R2.
Yeah.
So if 4
Yeah, so at steady state, this will be the velocity, omega 1 r1 and omega 2 r2. So you'll get something like this, right? But if omega 1 is much, much larger than omega 2, then what happens?
They'll be discontinuous. Or,
So it will be like the one we are doing right now.
though it will be the one like we're solving right now. Because what we're solving is omega 2 is 0.
Yeah.
Right? Omega 1 is very high. So it will be, if the fluid element near this becomes unstable and starts thrown around, then it will form these cells. Okay? So this is an unstable configuration. When the inner cylinder rotates faster than the outer cylinder, it's an unstable configuration. So there is a critical rotational speed above which the flow will go spontaneously from 1D to 2D.
So we have an R component and theta component.
You will develop an R component and theta component even though you don't have one in the beginning. Yeah, exactly. Okay, any other questions? Okay, let's just solve this. Where do I go? Study. Oh, I guess it doesn't allow me to study it. I'm learning with you guys, so I guess I need to build the mesh. That's about 11,000 cells, and you can, of course, you know how to blow it up and see what the structure is like. It's fluid mechanics. It knows that there will be a boundary layer, so it puts automatically more cells near the region away. It's coarser. It doesn't show what? I guess I didn't add the study, that's why. Because I need to specify, I need to add a stationary study, right?
Can we take a look at the mesh on the top or bottom?
Yep.
Supposed to be the same as. Yeah, that's what I expect.
If you had a wall on the top,
Yeah, it would be.
then you would see a boundary layer there. Okay. So this is how I guess artificial intelligence is being built into the software as time evolves. That is, once you know a certain type of behavior exists, you just code it and it's there forever. We continuously keep on improving. If you look at COMSOL in version 1 and version 5, it's a significant improvement in the way that the software is constructed.
Still, that's manually. So it's a manual intelligence.
What do you
It's
mean?
not artificial intelligence.
Yeah. What is artificial intelligence? Right. It is a learned behavior, right? The question is, does it automatically learn and apply it in every situation that it encounters? But it is programmed.
So there's a concept out there that they're beginning to, I think, implement.
Hmm?
So there's a concept that they can still apply that they're not yet applied. The
Oh,
neural
that's what you call artificial
yeah,
intelligence.
deep learning.
Deep learning, right? But if you, I mean, I've just started looking at deep learning and what to see what it is. It is essentially neural network. The
Yeah,
deep learning is nothing but
yeah.
neural network, and it is absorbing the patterns in the input and storing it in a certain pattern in the neurons, and then when it sees that behavior, it predicts a certain type of a thing, right? And that's coming. In all the software that will come. The software now knows about hundreds of thousands of material properties, right? If you can achieve pre-built geometries, it will be a very easy task to build complicated equipment design in a matter of minutes and get solutions to these problems fairly easily and fairly routinely, I think. But these are baby steps of artificial intelligence.
Because it's already being implemented in material design, right?
In material design.
Yeah. In
In-
DLT scale. Neural networks.
Yeah, I don't know about that. How do they do it?
So they put a descriptor and then you train it that how different materials interact on the DLT scale, high ab initio scale, and then the computer takes over and tries to estimate new materials, same atoms, and how they will interact afterwards.
Has there been any new discovery out of that?
It's been there for 6 years. There's a program actually that does it all.
Okay, but has there been a new material discovered and synthesized?
Not synthesized, it's computational.
Computational, okay. Because that would be the ultimate test of that kind of an approach. And I think it is fascinating. It is fascinating time. It's in the domain of feasible approaches, right? So you can program a computer to automatically synthesize new materials in the computer, and then the question is, can the real chemists synthesize the same thing? And if they do, then the AI algorithm gets even more credibility that it actually worked. Right? It only accelerates the pace of innovation, I think. All right, so let's see now whether we can compute there. So you go into convergence plots and see what's happening. Right? Yeah, question.
So we add symmetry boundary condition for having infinite
Right.
cylinder, right?
Right.
What is the difference? Because the equation for symmetry boundary condition was no force at the boundaries, right? No tangential force and no normal force. We have a free boundary condition. One of our options in boundary condition is so what is the difference between that one and this one?
In some cases, they are the same. We can go and look at what equation it imposes on a free boundary. A free boundary is one where you have a free surface, a liquid in a tank. On the top surface, you have a free surface, right? So you would have a constant pressure, and then there will be no normal velocity, but there could be a tangential flow. But the tangential stress would be matched on both sides because you have air on one side and water on the other side, right? So that would be equivalent to imposing, for example, mu1 du1 dn is equal to mu2 du2 dn. N is a normal derivative, for example. So this is at a tank with a free surface. Okay? So the shear stress on both sides is the same. Okay? But because this is air and this is water, you can say that the viscosity of one is close to 0 because one is 1,000 times smaller than that. Then you're saying that the gradient of the velocity is 0. Then it becomes the same as symmetry boundary condition. Okay? But in the symmetry boundary condition, whatever happens below happens above. That's the implication. Whereas in a free surface boundary condition, the gradient is 0. Okay? And the impact of that on the equations would probably be the same. So now we encounter the very first problem. It says no solution found. Okay? That means it is having convergence problem. Okay? And what you see in the convergences is actually converged. Right? The residual error has gone from 10 to the 0, 1, or order 1, 10 to the minus 9. This is an acceptable solution. But the tolerance has been set so tight that it says it has not met the tolerance, the default tolerance. Okay? So you need to now learn about algorithms. What kind of algorithm does it use? What kind of tolerance is reasonable? Or can I give it a better initial guess? All these can help. What better initial guess can you give for this one? What was the initial guess? The initial guess that it had by default was 0 everywhere. So on this folder, if you have to come up with a good initial guess, what would that be?
So U5 would be something.
U5 would be a profile that corresponds to omega times R. Okay. Now, we need to do some homework because I just was very careless in specifying my conditions. In wall 2, I specified the condition as, where is it? VW as 1, right? So I specified VW as equal to 1 meter per second. So what is omega? Omega is VW divided by R, which is 1 divided by 0.2. The inner radius is at 0.2, right? Which is 5. Right? So if I specify the initial condition as 5 times R. R is the variable for the radial coordinates. It tells us that by using these symbols, right? So I can use the variable like just like that. So it will automatically, when r is 0.2, this will be 1, inner velocity will be 1, and the outer velocity should be 0, right? But let's try this one and see whether it'll work.
So in this case, time dependent will just talk about the unsteady state profile.
The time, if I pick the study as time dependent, it will talk about unsteady state profile. So in which case, this initial guess that you see will be treated as initial condition. Then it would work. In fact, that's one way of getting to steady state would be to pose the problem as transient problem. Then the meaning for initial condition is it is truly at time t equal to 0, velocity everywhere is 0, which is a feasible operating condition. And then you rotate the thing and it will control the step size to control the error. Right now it's just making a guess and solving for a set of algebraic equations to satisfy the differential equation. In that case, it will solve a set of ordinary differential equation matching the error at every time step. So that's not going to work because
So this
Yeah.
convergence plot is with a linear line in between. It should have stopped there.
where? Which one?
Yeah, that part. Yeah, where you point.
But if the tolerance is somewhere here, it will say it doesn't match, so it will just keep on iterating. Right? And it is now at the noise level, round off error, 10 to the minus 9. Right?
Can't we change the tolerance requirement?
Hmm?
Can't you change the tolerance requirement? Then
You can. You need to figure out where it is. And I haven't prepared to, I didn't search for it this afternoon. But let me just see, let me fix this problem first. Because this velocity of v5 as equal to 5 times r is not the right profile. Because I want this to be at the inner cylinder, I want the other one to be 0, right? So I need to actually make this as v5 equals ar plus b, and I figure out what these two boundary conditions are. So when r is
0.2.
0.2,
Because 0.1, what is change? When R is 0.2, it's 1.
0.28 plus b, and then I need to go on
0 and 0.4.
Is it 0.4? Okay. 0 equals 4a plus b, right? So it is 1 is minus 0.28. So a is minus 5, and if a is minus 5, b is 0. Right. So let's try that and see whether it works. Minus 0.5 r plus 0.
Yeah,
It's not zero. It's not zero.
Because the second equation is not satisfied.
B is 2.
B is 2.
B is 2.
Adds up, yeah.
2 minus 1 is 1. Yeah, correct.
And then
Minus 5r plus 2, correct? Let's try that. Whenever this happens, the error went down in one step by
I think
this.
it went down in 6 steps.
But yeah, 5, 6 steps. But after that, it doesn't go down. Now, there is another trick. There are lots of tricks that one can continue to kind of learn, right, to make these conversions. And this is a common problem that you will face. Sometimes, like in this case, the problem comes from the fact that it is a nonlinear problem. It's solving the full Navier-Stokes equation. Okay? Sometimes it comes from the fact that the problem is unstable, physically unstable. Like when you increase the rotational speed beyond the critical Taylor number, you will find these cells. And that's going to take a lot of iteration to jump through that transition phase. And so you don't know what is causing this instability, in this convergence problem, whether it is numerical issues due to nonlinearity or whether it is physical instability. Okay, and no artificial intelligence has come in yet to address that, but one day it will, I think. So it is not going to converge this time also. It's already going through the same phase, right? 10 to the minus 9, and then it is not. Oh, well, it went up to 10 to the 11, it just came back. That's the estimate of the error. What is that estimate of the error? The difference between the left-hand side and right-hand side of the Navier-Stokes equation. Okay. To me, if that's perfectly acceptable, I would accept it, but I just need to figure out where to go and set the convergence criterion to a larger number.
The relative tolerance?
Yeah.
I think is in.
But I will show you.
Stationary solver.
No.
At the bottom.
No, I want to show you before that another trick that you can do. Neglect inertial terms. What does that do? It gives you the Stokes equation. So now what you're doing is, instead of solving v dot del v rho equals minus gradient of p plus mu del square v, you're setting the left-hand side equal to 0. Why is that a good thing? It's not a good thing in general, because in this case you do have inertial term, but it takes a nonlinear term away. This is a linear term, right? A linear term, when you discretize it, you're going to get an AX equal to B type of equation. One matrix inverse, it will give you the solution, okay? So this should not have any difficulty in solving, but it will be the wrong solution because you're solving the wrong equation. There it is, right? You'd immediately solve for it because, and what do you see? You do see exactly the same as you would expect. The gradients of 0 here, and it's as if it is continuing infinitely, and along the radial direction the velocity is highest, 1, and 0 at the other end. Any section you get, you'll get the same thing. Okay? So it is truly a one-dimensional solution. Now you do the trick of activating that. See, it says creeping flow. Creeping flow means this is 0. I'm solving this equation, creeping flow equation, Reynolds number 0 equation, fine? So you go back and take that out. Immediately it changes to laminar flow. Now it's going to include this term. But what it does is it has the correct velocity and pressure profile for 0 Reynolds number. So that's a good guess, right? So what you need to do is, the trick is, don't solve it, but update the solution. There is an option there. Update the solution means start from the previously converged result and do some more iterations with this term included now. Okay? And that will converge without any problem there. Right? So 10 to the minus 15. So the error was somewhere in this region. The criterion was somewhere in this region. That's why it had to do.
So can we check like the one we ran and see if it was a good result?
Whether this is a good result?
Like what we got for 10 to the power minus 9, was it a good result compared to this?
That's a good question. But I cannot demonstrate that to you because I don't know how to recover the solution. We'll try.
Does it show the result?
Yeah, it does. I don't know whether it shows the result, whether it saves the result and gives us access to look at the result. I don't know the answer to that. It may, but we can look at it. Okay, so now you can look at the results. So there are data sets, and this is what I want to show you. This is just a visualization gimmick from COMSOL that shows that it is truly axisymmetric. It didn't really solve in the domain. It solved only in one plane, but it projects it for you by rotating that to show that it is axisymmetric. This is what axisymmetry means, right? Around that, everywhere it's the same velocity. So in 2 dimensions, up and down it's the same, in the angular direction it's the same. Okay? Okay, let's now try to answer your question. Where do I go and
We can go into the results and just try to save this one, the current one.
go to the result?
Solver configuration
Yeah, so that's the folder that has these solution parameters, right? And here pressure and velocity field. So
I think all these values would be in the results section.
advanced. No, we're trying to see how to control the tolerance first, and then we'll go and see. We will reset it so that we solve without convergence and then look at the results. So there are two issues. So here there are lots of algorithm-related issues, and we will understand that only when we look at numerically solving the Navier-Stokes equation.
Assembly settings.
Assembly settings. Assembly settings refers to the fact how do you assemble the matrix. There must be something about tolerance somewhere.
Can you go to the properties section? When you say the settings, there should be a property. There's one on the right top.
Oh no, properties doesn't have anything. It's just a box that you can put any comments you have. Every one of the folders has a folder property section for you to comment. So there's really nothing in that. It's the settings in every folder that's important. So you need to go, yeah, there it is. Initial damping factor, minimum damping factor, 10 to the minus 6. Restriction, maximum number of iterations, you can increase that. Terminating technique, tolerance, that's what we have. But where does it specify what the tolerance value is? Iterations or tolerance. Number of iterations, maybe make it 1000. Tolerance factor. Residual, and where is the residual value? Okay, let's just compute this. Okay. You can play with the mesh also. Mesh also affects the convergence, right? But here we are into the situation again where it doesn't converge, right? So we can see whether it stores the solution and access the solution.
Click on stationary solver. No, it's click on fully coupled.
Do you know how to stop this when you get into this difficulty?
X on the right at the bottom right.
Cancel computation. Thank you. You guys are good at it, so why am I teaching you this?
Stationary solver. No, at the bottom.
Where? Oh, there. Yeah.
Okay. It's relative tolerance. You can, yeah.
Yeah, but that's 0.001. But we are going way below that, right? So maybe you can try increasing this,
Can I try?
and then see whether it will help. But yeah, so when I increase the tolerance, it deemed as convergent, right? And I have the result, which is a convergent result.
Can you check the convergence plot once?
Convergence plot,
-3.
right?
1 minus
Right. So you get an idea of how to manipulate it now, right?
10 to the power minus 3. The value is 1 multiplied by 10 to the power minus 3. So
Right.
when you had 0.0.
Right, yeah. So the challenge now in your next assignment is to do the same problem, but go through this transition. So I want you to solve this problem for different values of rotation and speed, and I'll give you the definition of what a Taylor number is. That depends on the gap width, the kinematic viscosity of the fluid, and the internal rotational speed. And when that number is 1706, if it is below 1706, you should get this solution. If it is above 1706, you'll get these cells. Okay? And I want you to transition through that.
Okay. When you did the fluid properties like density and viscosity, is there like a library built-in console where we can
Yep.
pick the substance?
There is from material. Okay? From material. And then you go into the materials library here, and then you can pick whatever material that you want. I think it should give you. I haven't really played with this, but that's how.
I think in the material section.
Maybe we can
write
do add material.
Write all the big.
Yeah, add material, right? Yeah. There. Okay, so that way you'll pick whatever material that you want from there. Okay. Now, a question for feedback. Is this kind of useful? Is this enough so that you have sufficient expertise in MATLAB, in COMSOL, to be able to continue to do assignments, next 2 or 3 assignments? And then I'll go into the concepts of dealing with the equations. That's good enough, right? So we'll do a couple of problems that we talked about, Taylor-Coed being the next one, and then flow past a cylinder maybe, and a few other, the flow in a channel, bifurcations, etc. So with that, we stop on this and go back to the slide. And I guess I have only 5 more minutes. So I wanted to show you what equations actually COMSOL solves or Fluent solves. These are taken from Fluent manual. Okay. So the continuity equation that we derived in Fluent and in COMSOL is written in this form. This is for compressible fluid. Density is not a constant. For incompressible fluid, this term will drop out, this term will drop out, and you get del dot V equal to 0. But they also have a source term. Okay? And you will see this as a pattern of templated equations for solving a certain type of template. And the template that occurs most often for mass balance equation is something like this. And for momentum, heat, and the species transport equation, it is something like this that you see here. Now, when I say axisymmetric, when you expand the equations have what he calls x, what we call z, and then r. So there is no phi dependence. Okay? So this is different from expanding that equation in Cartesian frame. So most of these solvers have both the options, solving it in Cartesian frame for any complicated geometry, and those that have axisymmetry property, solving this set of equations. And that's why you need to check that box to say that pick this set of equations to solve axisymmetry problem. So that is a continuity equation with a source term. A source term, we will see when you discretize these equations, just appears as the right-hand side of your Ax equal to B. B is your source term. And that source term will come either from boundary conditions or from distributed source in a flow domain. Okay? For example, you could have, and this is happens in reservoir engineering, but also in some nice simple fluid mechanical experiments. Suppose I have a thin disk, and I have a hole, and I'm injecting liquid through that, and there is a gap here, so the liquid is open to this, and it's going to come and spread. What kind of flow pattern would you expect? Do you understand what the problem is? There is a gap between 2 glass plates, okay, and there is a hole, and through a tube I'm injecting the liquid. Right? So the liquid will fill and maybe advance like this over a period of time. Right? Now if the initial disk is filled with oil and you are displacing it with water, then you will have something called a fingering instability. So what happens is the water that displaces will actually break and form fingers through this. I don't know whether you have seen these kind of fractal structures that will go through. So there is an interface between a gas and the oil and water.
Can you do this without implementing electrostatics?
I mean, if the physics doesn't have electrostatics, you can solve it as it is, just Navier-Stokes equation. But if the physics has electrostatic interactions, then you can include them as a source term in here. Okay? That algorithm is essentially built on the Navier-Stokes equation, but it calls for a different set of computational schemes that tracks the interface, front tracking schemes or level set schemes. COMSOL has built all these into the software solution. You just need to know how to pick the level set method and pose your domain in such that you can look at such displacements. But in this case, you can treat this as a boundary through which you are injecting, or you can treat this as a source. That's what I wanted to talk about. So take the inner part of this, and that's a mass source. From that, you are just injecting the fluid. Then you can add this to the mass source term. You need to define what that is, and in what cells you are injecting that mass source. Once you discretize it, you can pick a particular cell and say somehow magically some material is appearing there, and you can inject it. So you can have a source, you can have a sink if it is negative. Okay, so that's a very general formalism that allows you to specify source and sink in any boundaries or any interior domain. So this is the Navier-Stokes equation with the shear stress term, the gravitational term, and any source term that has electrostatic, electromagnetic forces, etc. And tau is your shear stress expression here. So the laminar flow model in COMSOL solves these two sets of equations. Now, for 2D axisymmetric, it is the same equations in an expanded form in cylindrical coordinates. Okay? This is without swirl flow. So you have only two components, Vx and Vr. They are functions of r and x. There is no phi dependence. If you check the, so you have the x momentum equation and the r momentum equation. But if you check the swirl box, then it adds the third momentum equation, which is, I guess it's not here. So it would be the V phi momentum equation. That looks very similar to this, okay, with the gradients in the phi direction. Now, all these equations look like this. This is what I meant when I said a templated form for solving numerically. If you write one subroutine for solving this class of equations, you can use it to solve each one of the momentum equation components, the energy equation, the species concentration equation. They all look like that. So phi k is the variable that you're solving for. It could be u velocity, v velocity, w velocity. It could be temperature, it could be concentration. Okay? And this is your advection term. And this is your diffusion term. This is your diffusion coefficient. Heat transfer, that's the conductivity, mass transfer, that's the mass diffusivity, or momentum transfer, that is the kinematic viscosity. Okay? And this is the advection term. This is the quantity you're solving for, but it is affected with that velocity. So when phi itself becomes u, then it is a nonlinear term. But when phi is some sort of a composition, that is still a linear term, okay, because u is coming from momentum equation. And you have a source term. So they have generalized it, okay, going from 1 to n. COMSOL, Fluent, they all essentially solve that one equation. If you figure out how to discretize that, it's a convection diffusion equation with a source term, you have a solver developed. And there are billions of dollars made by solving that equation. ANSYS is a huge company with $1 billion turnaround every year, right? But this all started in the 70s or 80s when they wrote a preliminary code. When I took a graduate computational course, I actually would write a code to solve for this, at least in 2D. Okay, that would be a requirement. But nowadays, we're not requiring you to do that, just learn how to use COMSOL. But that allows us to explore a number of other physics-related problems, physics-related posing of the problems. So this is a rigorous formulation for single species to multi-species by single-phase flow. Okay? Single-phase flow, you can have any number of components, a multi-component mixture in a single-phase, miscible fluid, methanol, water, isopropyl solution that's being mixed in a reactor or a configuration governed by this equation. Okay? So the velocity field is all the same thing with phi equals v, and concentration field is all the same thing with phi is equal to c, or the thermal field is all the same equation with phi equal to E. And you should understand the coupling between these equations. Which equation affects what? The velocity equation affects all species transport, temperature or concentrations, because velocity appears in all of them. But whether the temperature affects the velocity field depends on whether the source term that you have here, rho g, for example, is affected by concentration or by temperature. Okay? So that coupling you need to understand. You'll probably see one or two examples in console on how to set up this and through an assignment that we are make you work on that. So density in the momentum equation depends on T or concentration. Then we have a two-way formula. Okay? And we already talked about boundary conditions for these. And there are lots of similarities between momentum, heat, and mass transfer. Okay? So that equation is the template that is solved in a very generic fashion in most commercial software, OpenFOAM, StarCCM, COMSOL, Fluent, etc. So we will learn how to discretize this later on in the course using finite difference, finite element, finite volume to understand how the discretization works in different framework. Okay, COMSOL uses finite element, others use finite volume mostly. Okay, I think we will stop there and continue on Wednesday with this for multi-phase flows. Okay.